Hi everyone, welcome to this session. I got a question. It was a very good question. The participant is asking how we size the column, how we determine the nodes. So my explanation was because of three reasons. The first reason, you would like to use your column efficiently, which means that allocate a certain distance for each strut. So if the force is low, you allocate smaller distance. If the force is high, you allocate larger distance. So that is my first explanation. The second explanation, you don't want a central node. You want to shift the node as much as to the left or as much as to the right to optimize your angles, because that's how the stress will behave. Stress will take the shortest path. For that reason, that justifies those two nodes as my second explanation. My third reason is the ease of checking it, the nodal zones, because if you only have one node, it's going to be really troublesome to do the checks. You want to isolate the forces as much as possible. That will really expedite your check. So because of those three reasons, whatever example you look, whatever procedures you follow, you will see those multiple node situations. And the trend is like this. So you might see some older models maybe not really doing this separation, but the newer models, definitely we would like to separate the nodes. I would like to add another check. We designed the pier cap, but we didn't really design the column. I'm guessing you would be using your software for column design, which is, you don't need a strut-and-tie for column design, but just, since we finished this, let's just run a quick calculation to see the column bearing. I'm only going to be using the compression for the column, and I'm just going to do a bearing check pretty quick to see whether the column is sufficient or not. So this is a really quick column check. It is same as bearing check, because you might consider that to be a bearing plate. There is really no difference between a bearing plate or a column. So same as bearing plate, it's just the strength changes, but the process the same. Bearing plate check. So limit stress, so it's going to be CCC. The node type would be, again, compression, compression, compression. Typically for that, and limit would be 0.85 F prime C. So I'm going to be checking node E. Let's just do this check. Let me grab some notes. I don't want to make a mistake because I use maybe too many codes. Which one I'm using, I have to really check the multipliers for that code. All right, 0. So I'm starting, call this BR, concrete reduction factor 0.70, 0.85 times F prime C. I see F prime C 35 megapascal, which is pretty much, that's all. And then the distance, what I allocated was 143 times 2, which is, sorry, not divided, times 2, 286 millimeter, times, you have to look at the column thickness. I see specified by 750, 30 inches thick, 750 thick. So based on that, I can get this quick check to see where we are at. $4,185. Oh, that's quite a lot. $1,190, no problem, tons of capacity. So this is much larger than 1190. So the allocation that 143 would be sufficient. This is really important check. Sometimes it's not. If you have a narrow column or a thin section, it fails. So I'm glad I'm checking this additionally. Also check the other one, because other one I see tension for the other node, which is CCT limit. It was 0.7 F prime C, and this is at node F, and for this one BR 0.70. I'm sure it's going to pass. It's tons of space we allocated. 0.70, 35 megapascal, and then we allocated more space because it's a larger force. 233 times 2, 464 times 750. So definitely this is going to give a huge capacity. Let me check. 5968. I mean, you can approximate it as a square column from the very beginning of the calculation. So that would be my suggestion to you. Do not start with a circular column, because I mean, if you want to be super accurate, I don't think it pays off to be super accurate in this situation. So let's say you have this one, you are putting the node here, then you know, if you want to be super accurate, calculate these areas and then do your calculation accordingly. And maybe another node which uses this one. I'm guessing you want larger, so I'm guessing this node would be shifted here. You want a larger area because you are really losing out of area. So definitely you can go with circular, but more than often we just idealize it as a square column. Also, H2 has some suggestions for this idealization. It's not a rocket science, it's some simple conversion. So you get the same area and then you just do it accordingly. So you can do, this is definitely more accurate. So if you have resources, go with this one. If not, go with the other one for the node determination. If you are having tons of capacity, it doesn't pay off to be super accurate. So you can always go with a rough model. But if you feel that it's really tight, column is something which is governing because of, you know, architectural reasons or some other reason, column is a little bit too small, then maybe go with a more accurate representation. Yeah, that's another good question. Dead load is really up to you as the designer, and I'm working with multiple companies and they have certain approaches. When you do a structural analysis, even in the sectional method, you have to put that dead load onto the system. So nothing different. So whatever approach you use for your sectional analysis for putting the dead load, the thing is that you want to account for, these are factored load. So it has to consider dead plus live. If you have impact contribution, you have to have those. So using your procedures, however you distribute the dead load, consultants put half to the top, maybe they allocate the other half to the columns. If you are allocating some dead load to the columns directly, then it's not going to stress your struts. So putting all the dead load to the top would definitely be the most conservative solution, because you are using struts to transfer the entire dead load. Hi everyone, welcome back to the second hour. In this hour, I'm going to show you a couple of tips in terms of how to make your models more efficient, maybe fill some knowledge gaps in terms of more advanced modeling techniques. This is coming from ACI. I know you don't use ACI, but ACI documents are very well detailed. They are colorful and they show lots of geometrical information which is applicable to any code, any strut-and-tie method. So these are some screen captures from ACI PCR 445.2-21. So this is a new document, relatively recent document. So if you look at this, this is how ACI is defining a deep region, same as how we defined it. Disturbed region, you just go H away from the disturbance. It could be a change in geometry. Again, this is a change in the geometry. It could be an opening or it could be a corner. Again, geometry changes. You can see this is a support condition situation which creates discontinuity. Pretty much the same idea. So section thickness is H. You just go H from both sides and that's your disturbed region. Corbels are pretty famous because the entire corbel ends up being a disturbed region. It requires either empirical solution or strut-and-tie method. You can read the narrative. You can see the developments, which is the historical development, which I provided you already. This also discusses a couple of strategies for model development. In the first attempt, if the angle is not too shallow, it always makes sense to use a single strut and see whether it passes or not. That should be the first attempt. Again, the code is using the stress block approach, calculating the moment to help determine the centroid of the rebar as well as the centroid of the strut. So you can see this approach. So you do this first. You never start with a complicated model. If it fails, then you try the second version. So the second version would be to improve angle, because angle dictates pretty much everything in this method. This is going to have a steeper angle. Lift it up, shoot it again. This is sort of a slender behavior. You know, if you do this, it's slender. Probably your shear span to depth ratio is around maybe 2.5 if you are doing this. If it's a new design, you can make it deeper. You can make it deeper to avoid this inefficient mechanism in terms of lifting the same force. So increase the thickness, increase the age of the section, make sure that your angle is good and you can directly go without any ties or any straps. So that is the approach. The third one is even more refined. I don't recommend using this one for a new design, because in a new design you have lots of flexibility. You can design it in any way you like. You don't want to do a super complicated design. Of course, this is going to give you a larger capacity, but for getting 10%, 15% larger capacity, there is a big chance of making mistakes with such advanced models. So if it's a new design, I would strongly recommend either this one or that one. This would be more appropriate if you have an existing system and you are checking the capacity and you would like to get the most accurate, most refined model. Then you would go with such a refined model. This is an indeterminate truss. You would need to make some assumptions, because you cannot just run SAP 2000, because indeterminate systems need cross-sectional areas. Each member you have to determine what's the width, what's the thickness, so it becomes rather complicated to do indeterminate analysis for strut-and-tie. This approach is a little bit more assumption based, which is I would much rather going with this one as opposed to this one, because let's say this is an existing system, you have some light shear reinforcement. You calculate the capacity of that light reinforcement, which is tie BH, you put that at the centroid and you size it, so you send this force just enough for that tie to be able to lift it. So in other words, you determine the ratios. Move a portion which is going to be just enough for the tie to be able to lift it without any overload. Whatever remains, you shoot it from the higher strut. You did the first model, it failed, right? You are doing the second one, you don't have enough stirrups. In the second one, now this fails. The first one, this failed. This is an existing system. Then my third attempt would be this one. In this case, I proportion it such that I would send only the tie capacity to this one and whatever remains to that one, but I'm pretty good with the angle because I'm also improving the angle, so more than likely this might pass. If your original model fails badly, let's say you have 100% overload, maybe nothing passes. So don't expect to gain huge capacities by going to a more refined model, but if you have maybe 20-30% overload, something more manageable, then you can always refine and try to get larger capacity out of the system. This is definitely most complicated. You need a computer for doing that, so I would go with this one. I gave this one to you as a larger handout, so you can read the narrative, how this is developed. This is again a stress analysis. It shows how stress spread. It uses larger concrete distances, but always we check it at the narrowest location. You remember we determined some concrete thicknesses, and I always checked it just underneath the bearing plate. That's the reason, because stress needs to really go into that shallow location, so we don't check it really at a high location. We check it at the minimum cross-sectional location. These are, don't worry about these. These are ACI coefficients, pretty similar to H2O, but since you are not using ACI, you don't have to worry about it. Same, this is a deep member. This is how ACI is modeling it. So he's showing you the stress field. So nothing unusual with this one. It is very similar to the deep member which I developed. This is a pretty coarse approximation, and you see this is going with L/4. These are different node types, CCC, CCT. These are everywhere. Canadian code, European code, ACI, H2O, it's the same. Multipliers. ACI is a little bit heavy in terms of multipliers. Don't think ACI uses this, because ACI multiplies this with something else and the result becomes very similar to H2O. So it's not using 1.0 for CCC. It becomes again 1.85-ish for CCC. I mean, ACI has lots of multiplications. Some shear force limits. These are ACI sort of requirements for sizing it. Is the section is large enough? So you can do this, maybe not step 7, but maybe earlier. This is for sizing, preliminary design. You can see ACI showing you D region, B region distances. This is more important, I think. This is a question which I got during the first hour, how to proportion nodes. As you can see, never use a single node. Always, this has a single load, of course, right? But you divide it in a 2-node situation, trying to spread it as much as possible, because the left one, the leftmost it is, the better the angle is, right? Again, this one, you want to get it as much as to the right, but it looks like the force is heavy for this one, so this is based on this proportioning. These are formulas actually, so you can use this to determine how to proportion load into 2 struts. Typically it goes 2, but if you have a support or something here, then you might do 3 divisions. One thing, you might split this into 3. So it's pretty similar to the column distribution. It's the same thing. This could be a column. There is no difference between a bearing plate, column, anything that supports a member. And this could be upside down. Don't think it needs to come from above. So I think the example we did was something like this. So you have a column here. This is how you would divide. This is pretty much what I did in the previous example. This is also giving you the distances right away, which is the same as the handout, but this also, they did an experimental test on a specimen to show the accuracy of strut-and-tie method. They created 4 different models for the same system. Each model will have different efficiency. Some would be more efficient than the other one. This has 2 disturbances. The first disturbance is the geometry. The depth changes. The second disturbance is opening. Opening is definitely more difficult because you need to cross an opening from both ends, and you can see the models developed. Looking at the models, which one do you think would be the least efficient? Looking at these, generally the more concrete you use, the more efficient the model becomes. For example, B, essentially you are creating a beam here, not really using this part, so your effective depth is pretty much this much, right? You are not using the entire beam, as opposed to C is really using the entire depth of the beam, so I would expect C to be more efficient than B. C looks like a good model because C, if you look at C, this is pretty much orthogonal, because remember, this is a common mistake which I see from consultants when I review their model. They end up with some diagonal ties. You know, diagonal tie should never be a part of any model unless you put diagonal reinforcement, which is unusual. So, you know, in a bridge member, we don't really put diagonal reinforcement unless there is some special situation. So the reinforcement typically horizontal. So if you look at this one, if you design this, it's going to be super easy. You are just going to be laying some horizontal reinforcement. Yes, it would change elevation a little bit, which is fine. You would be another layer of reinforcement here, perfect, and some stirrups in this region and in that region. So in terms of practical applicability, this model is pretty realistic. If you look at A, you see some crazy diagonal ties, then you gotta put that reinforcement. So it's going to be a major difficulty because you need to extend the bar diagonal, another diagonal bar, and more than likely you would get a call from contractor asking modifications from your design, and you would have to redesign. Let's look at the experimental results. They created 4 strut-and-tie models, and based on these models, they put the reinforcement in, right? So 4 different designs based on 4 different strut-and-tie models, and they tested them under point load application until failure, right? So if we look at that, this is the load deflection result. This is the displacement, this is the load. And if you look at this, C is the winner. C gets 1250 kilonewtons, which is much larger than what B gets. B gets the bottom lower bound in terms of capacity. So B also softer model, stiffness is lower because again, B, you are not using the entire depth. So it's sort of effective depth is shallow. It's a small distance, so it's a softer model. So C becomes the most efficient, the higher strength. A is also pretty good. Definitely A is good, but the issue with A is reinforcing. So you have to put some diagonal bars. That's going to be a trouble in real situation. B also works, of course. It's less capacity, 750, so it's significantly less. It works. D also works, looking at D. So this is the experimental results. And if you look at strut-and-tie results, yeah, this is the test. This is strut-and-tie ACI. This is STM. And as I told you, STM will always be conservative. So test is giving 72% larger capacity. So you have almost double the capacity. So your STM for A is super conservative. For B, your STM is 30% more conservative, and these are on top of the ultimate limit state. These are after you apply all the factors and so on, which already has a good factor of safety. So this is on top of the typical factor of safety. C, 50% more capacity you would get in real life than STM, and D would be similar. So that is 50% more capacity. This one, it is extremely unconservative. The specimen fails at 40% of the STM capacity. So you calculate the capacity and it fails less than half of that load. It's a really dangerous situation. Nobody wants to be in that situation. The reason for that, they wanted to see the influence of crack control reinforcement. So they removed crack control reinforcement, which is the mesh. It's a heavy mesh, both sides, both faces, both directions. So this no mesh means no crack control. I want to highlight this. Again, you might have the best strut-and-tie model, but if you are having issues with your crack control reinforcement, you are not going to be getting that capacity. In real life, the capacity might be less than half of your predicted capacity, and it's going to fail. Or you would get some huge cracks under service loads, and it's going to be a trouble if you don't have that crack control reinforcement. So again, any one of those would work. You would get different capacities. And I get questions about strut-and-tie. What if we don't use it? What if we just use sectional method for everything? So the issue, when you use a sectional method, let's say you have a deep member. So let's say you need to put reinforcement at the bottom, at this location. You calculate this reinforcement. STM is telling you 10, number 10. Right, so sectional is telling you 20, number 10. So this happens, sectional is definitely, in terms of reinforcement, it's going to give you more, and you might say, oh, I'm going to be putting 20, number 10, and I'm not going to be bothering with strut-and-tie. Is this a good approach? That's my question. You use double, which is fine if that's what you want to do. Is this going to be a more conservative design? That is my concern. Probably not, because doubling the main reinforcement is good, but what about crack control? So fine, I mean, if you don't want to do strut-and-tie, go use sectional, but use strut-and-tie requirements, not the model development, but still put your crack control. So that's what I want to say, because deep members definitely need that mesh, both ways, both sides. So now, yes, this would be more conservative. It would be a good design. So never neglect crack control, even if you use sectional. You can also use maybe U-bars, depending on if it's a narrow section, you know, put some U-bars at the edges, which I did. So you don't have to run STM for every single deep member if you don't want to, but you can really make sure that your model works efficiently by following those additional steps, which I did in my solution: provide crack control, reinforcement, this and that. So those would be tremendously beneficial, which also exemplified by this example. The capacity with no mesh for a deep member would be, I mean, look at the numbers: 61 kips versus 290 or 250, or the minimum one is 183 and you get 61 if no mesh. So it plays a significant role, and ACI is pretty good. I mean, this type of experimental validation really shows it to practitioners, and for that reason, even though you are not using ACI, I included this. So what this is, strut-and-tie is for ultimate limit state. If you are using a stress analysis to develop the model, stress analysis will give you uncracked condition. So if you do a stress analysis, your tension zone would be at the bottom, which is fine. But after cracking, your tension would be shifted up. So you can also use a nonlinear finite element to get the cracked behavior, and you can develop the model for considering that cracked behavior, which is a little bit overkill at this stage. So these are a little bit higher type of modeling approaches. You should be more than fine if you go with elastic stress trajectories, and that should give you some good information. So you see it here. These are elastic stress trajectories. If you follow these, you will see, again, never a same node. You have to divide this. So again, you need to divide it into 2 nodes at least, and the node should be, so let's say we are developing a model for this. You need a line at the top, you need a line at the bottom, right? Divide it into 2. One node should be here, other node should be there. 2 node is enough because it goes into 2 supports. This is the same as the previous example. This is the elastic stress analysis. So again, strut, you see one strut goes here, maybe the other one goes something like that. You cannot come this close because you don't have any thickness. This is not even possible. You need to give some distance so that at that edge you have some width to that strut. So this one definitely will not work. It's not even permitted to do. So that's another strut. So you can do this type of approach. For example, I put that strut here. He's having that strut going here. This one is also having a similar strut. So you start from here and you refine it. I don't recommend you to go into such a complicated model, but you can use elastic stress analysis. First of all, 2 questions open for debate. How not to develop a strut-and-tie model? So my answer would be a new invention. So I strongly discourage anyone to invent a new model. So this is something to avoid. How to develop an appropriate model? Use your previous examples. You should have some solutions done before. For example, now you should be able to solve peer caps because we did it, you did it. You should be able to tackle peer caps. It's going to be more or less similar, some modification of it. It's not going to be radically different. For example, you can solve peer caps. You can solve right now deep members. You can solve deep members with point loads, etc. So look at your previous solution library. Look at your binder, what you solved. Use those previous solutions. That's the best approach. The second one, find solutions from other people. Guidelines, publications. So use published solutions. There are published solutions by ASHTO, by other organizations. They compile certain documents together and you see sample examples. Used, published, sample, question, solutions. So learn from them and then apply I mean, you should find something similar, but you are not, I mean, you have a unique situation. You are finding some similar examples, but not quite. Your situation is a little bit different. Then use elastic stress analysis along with some samples, along with sample examples, solved examples, which is not exactly, I mean, you have a solved example which doesn't exactly match and you are concerned about the region. So you do elastic stress analysis and see how the tie strut needs to be oriented for that region. So that is the other one. And of course, I mean, I'm sure you are doing this in your design projects. There is a senior, junior, have it reviewed by a senior person with experience. Also, maybe let's add another one, avoid diagonal ties, because in real life, we don't use diagonal reinforcement. So avoid diagonal ties unless you have a diagonal reinforcement. I have another example, which is example number 4. It is a little bit more advanced because it has three-dimensional model. So it has a three-dimensional strut-and-tie, meaning that you do two-dimensional models. I'm going to be looking at how the force spreads in the elevation, but also I'm going to be looking at how it spreads through the thickness. My intention is to solve this on camera, and I'm going to post this on my YouTube channel. This one would be like a public video, anybody can see it, but also I'm going to put, I already saved the question sheet into your shared folder. Anybody who would like to solve this can solve it. And also I'm going to put my solution, link it into the shared folder, so you would get that video, which is going to be publicly available. That is definitely advanced. I mean, the bending situation, if you go into a bending situation with strut-and-tie, it is going to be rather involved. I can show you some sample solutions. So in this example, it is a bend which is cantilever, as you said. This is intended to create moment, so there is significant bending moment which you cannot neglect. The general issue is similar to your question. You asked that question in the first hour. How do we size that column to determine those two nodal locations? You need to do some idealization with tension and compression triangular distribution. Put your struts and ties at the centroid. As you can see, he is creating two struts for this situation to not exceed the concrete capacity. Tension, you don't need that. Tension is neglected. He's not even showing the stress distribution for tension, because in tension we neglect, there is no concrete, it's just a rebar. So he's putting the rebar at a certain distance, which also needs to be determined. So the challenge comes from this situation. You have to determine, and it never passes at the first attempt. So I think he's also doing multiple attempts for this one. He's looking at the corner load, should be super critical, because if you do a stress analysis, you would see the stress would be really concentrating at the corner. So he's looking at that node, determining the widths for this situation. I can share this document with you, no problem. So take a look. I'm going to put that in the shared folder. Let me look what else in this one. This is yeah, these are the examples. I can share the entire document with you. Oh, third one is also a good one. So you can see this is an inverted cap section. He's designing with bending moments. He's doing a frame analysis because he needs to determine those triangular distributions. So it always comes down to this triangular distribution for moment. He's trying multiple things because you want to get the moment right. When you do those triangles, resultant of tension compression, when you take the moment, you need to get the moment. And he's doing a SAP 2000 analysis to calculate that moment in the column. And he's using a couple of attempts to get that done. So if you look, the trouble is typically at this node. Also, checking is a little bit difficult because it's a single node, so many struts and ties join at that node. You need to really zoom into that and see, determine the width. So there's some geometry involved, and I'm sure he did it at some location. Yeah. So you need to determine, this is the width for this tie, this is the width for that strut. So you need to determine all of these using a graphical tool because you are checking those. So it's always a trouble if you have multiple strut ties join at the same node. See, this is what I meant. So that's what he's doing, checking everything one by one. He's checking bearing. these are, I mean, these are not something I recommend you get into it right away, but maybe in later stages. Let me know, I mean, if you have any questions, if you have any complicated models, let me know. Might be able to take a look and give my feedback in terms of more advanced models. So yeah, that's pretty much it from me. I thank you very much for your attention. I hope you would keep continue. If you have any questions, let me know. Perfect. Thanks very much. Appreciated your participation, and I wish you good luck with your designs.